Hi there, this is a short version of a video reviewing the UM25C USB tester, a fake version of the UM25 and the UM34C. That video is a bit long to watch if you are only interested in the UM25C and nothing else. So here's an edit that focuses only on the UM25C and the test results. As with the UM34C, the real UM25C comes in a nice metal box to keep it safe, but it makes it hard to get out initially until the padding kind of wears in a little. The C in UM25C stands for communication and means that the C variant has an additional Bluetooth port to allow measuring from an app and also to record data in spreadsheet format. Apart from the Bluetooth port, which can be turned on or off, the C and non-C variants are identical. The menus and features of the UM25C are identical to the UM34C, and since I already went through the menus and how to use them when I reviewed the UM34C, I won't do it again. If you have not seen it, I put a link to that video in the description below. Here's just a quick run through, starting with the already familiar main menu and pressing next. We get the menu displaying the charge mode an external device may be using. Since no charger or battery is connected at the moment, the mode is unknown. This is followed by the capacity and energy measurement menu, and the menu to measure cable resistance in 2 steps. The graphical display of voltage and current over time, and finally the display setup. And back to the first menu. The only difference between the UM25C and the UM34C is the number of digits in the display. The UM25C uses 5, which translates to 1 mV resolution for volts and 0.1 mA for current, where the UM34C uses only 4 digits. This is an extract of the UM25C datasheet. The most interesting values are here, the voltage and current range, and on the other side, the resolution and the accuracy. It is interesting that RD Tech uses the rarely used promille designation instead of the much more familiar %. This might turn out to be a bad move because most people may easily misread 0.5 promille with 0.5% when it's really 0.05%, which is of course 10 times better. Same on the current accuracy with 1 promille, which means 0.1%. The other specs are identical to the UM34C, except that the current range has been extended to 5 amps, where the UM34C only went to 4 amps. Let's have a closer look at the UM25C. It is built exactly like the UM34C in an open sandwich, where the central PCB has the LCD and USB-A front and end connectors on one side and all the other components on the other side. A top and bottom plate protects the PCB, but the sides are open for airflow and to access the micro USB and USB-C connectors, as well as 4 buttons, 2 on each side. For the C variant, a second PCB with a Bluetooth chips are added to the bottom plate, which has an additional on-off switch. Since all the components except the LCD are on the underside of the PCB, it is sufficient to only remove the 4 screws holding the rear plate to examine the PCB and the Bluetooth board. The Bluetooth board connects to pads on the main PCB with 4 springy contacts. There are not that many components on the board apart from the big USB connectors. Key is of course the microcontroller, which is an ST Microelectronics 8S005C6. If that sounds familiar, it is because the UM34C uses exactly the same chip. The same is true for the voltage regulator 5333B, sitting between the controller and the big silvery electrolyte capacitor. The regulator is a low dropout type for 3.3 volts. Where the UM25C differs from the UM34C are these two devices here. The smaller one on top is marked as A810, and I think it's an electronic single-pole double-throw switch. That chip's not on the UM34C. The second one is marked CAQD, and I have not managed to find any datasheet for it. I guess it's an op-amp of sorts, similar to the one in the UM34C. I think that both of these are for current measurement, because for 1 mA resolution, the voltage drop across the current sense resistor changes by just 10 microvolts. The voltage drop is probably amplified by the op-amp, and the other chip could be used to change the gain and thereby implementing two ranges. Lastly, we have the current sense resistor, which is a precision 10 milliohm type, and the four big contact pads where the Bluetooth board connects. They are marked RXD, TXD, ground and VCC, as you would expect. Four smaller pads are marked VGRS and probably for programming debugging. Moving to the Bluetooth board, you can see the antenna, a PCB trace to the left of the DXBT18 chip. There's another one of those tiny A810 chips and another voltage regulator next to the on-off switch. The analog to digital converter in the microcontroller is very fast, but it only has 10 bits. 10 bits is definitely not good enough to meet the resolution and accuracy specs of the UM25C or the UM34C for that matter. My guess is that the firmware uses oversampling and averaging to trade update rate for more resolution. Another issue is that there is no reference voltage source integrated or externally on the PCB. Instead, the ADC reference input value is connected to the 3.3 volt rail coming from the regulator. That regulator isn't linear type. It converts anything above 3.3 volts into heat. That means it gets rather hot, especially if high display brightness is selected too. There's a temperature sensor right next to it, and the readings are shown on the display. I am suspecting that this feature is mainly to allow the firmware to compensate against drift of the reference, because by itself that temperature display is rather meaningless for a user. Comparing the voltage display of the UM25C with a 6.5 digit Agilent 34401A multimeter shows that the UM25C and the multimeter track so closely that the two lines are on top of each other. You can see that the error on average is just 0.01%, and at worst stays within plus minus 0.03, which is better than the promised plus minus 0.05. For technical reasons, the verification of the current readout happens in 3 ranges. This is why the blue line has 3 different gradients. The red trace of the UM25C readout is again so close that it's completely covered. If you recall, the current error is supposed to stay within plus minus 0.1% plus 4 digits, and as you can see, it is extremely accurate, much better than the spec for most of the range. The only time it starts to exceed 0.1% is at the very low currents, which is mainly caused by the way the error percentage is calculated. In any case, these are just 1-digit variances and still in spec if you take the permitted 4-digit variance into account. This table shows the current consumption of the tester with and without Bluetooth at different display brightness levels and with the display completely off. As you can see, especially with Bluetooth on, there's quite a bit of fluctuation between minimum and maximum currents. If we just look at the average, which is probably the most useful value, the tester consumes just below 10 milliamps with no Bluetooth and display to just above 32 milliamps with full brightness and Bluetooth. The lowest voltage the tester could display was 3.862 volts before it shut down. Once it shut down, I had to raise the voltage to above 4.2 volts to get it going again. The UM25C definitely meets its spec and is an improvement in both resolution and accuracy over the UM34C. There's no difference in functionality, which is really the same for both. If you can live with 4 amp maximum and 4-digit readouts, a UM34 or UM34C may still be a good option to consider. And this concludes the short version of the UM25C review. More details and comparison with the UM34C and a fake version of the UM25 are in the longer version. Thanks for watching.